The next piece that we need to understand in order to analyze circuits is what resistance is and how we design a resistor for whatever purposes we would like out of it. So first, to make sure we all have the right definition, we're going to consider resistance to be the hindrance to the flow of electrons. So anything that attempts to slow down the flow of electrons, that essentially resists current, is going to be resistant. So a simplified version would be obstruction of current, but anything that's trying to slow current down, and in doing so, converts that energy into something else like light or sound or heat, that's going to be what we call a resistor and the concept of resistance. Now, two things to understand. We have natural resistance, meaning every object to some degree has its own natural resistance. Electrons don't flow completely efficiently. It's not like there's objects that they just flow without expending any energy or anything like that. There is natural resistance, like wires themselves, even though it has very low resistance, there is natural resistance. We're going to ignore that. It's kind of like when we ignore air resistance and we ignore friction. It's there. Just understand that there's a small amount of resistance in any object, but the natural resistance is usually negligible, and we can essentially assume it doesn't exist. What we are referring to, what we will be looking at, is the intended resistance, and that's going to be much larger. So that's the resistance that's designed into light bulbs, fans, appliances, etc. That's much, much larger than the natural resistance. We can't ignore that. The intended resistance of different objects is literally what slows the current down, and that's going to have impacts on the entire circuit. So to summarize it, just understand that there is a natural resistance that every object, even a very conductive wire, has, and we can usually ignore it, but it does technically exist. So if we do some labs and you notice that there's like small drops in voltage that you can't seem to explain, that will make sense later on. Okay, it's probably because there's some resistance in this wire, but we'll get to that in a little more detail later. I always like to introduce the waterfall analogy at this point to kind of explain how voltage, current, and resistance are related to one another. So in this analogy, this waterfall that kind of flows down into a river, the height of that waterfall is like the voltage. So the higher that waterfall is, the faster that water will flow, and the smaller that the height of that waterfall is, the slower it will generally flow. So you can see that the current in this river is directly related to the voltage. Or the flow of water in this river is directly related to the height of that waterfall. You have something like Niagara Falls, and the water flows very, very quickly because of how much water is flowing over and how much potential energy it has at the top of that waterfall. Then it's converted to the kinetic at the bottom, etc. Just like if I utilize a larger voltage battery, I'm going to get more current in the wires. So the voltage is kind of like the height of this imaginary waterfall, which has a direct effect on how quickly that water is going to flow once it hits the bottom. Where resistance comes in to anything that we put down, like a dam per se, that's going to slow down this current and convert it to something else. So we have hydroelectric dams, like Hoover Dam, that uses water to spin a turbine, and we convert that to electricity. So think of a dam as like the resistance. So the same kind of thing applies to an actual circuit. So we have a very basic circuit here. We've got the voltage source. That's kind of like the waterfall. The size of that voltage difference is going to govern how much current is going to flow through the circuit, much like the height of a waterfall is going to govern how quickly that water is moving by the time it reaches the bottom. The light bulb itself would be like the resistance, or in this case, like the dam. It's going to slow that current down, and in slowing that current down, it's going to convert it into something more useful. So in this case, it's going to convert the electric energy into light energy. And as a result of these two, depending on the size of your waterfall and how many dams you have, you're going to affect the current. So more voltage means more current, because that's like increasing the height of the waterfall, but more resistance means less current. That's like adding more and more dams in the way of the river. So you start to see there's kind of a balance here. We can adjust and design the voltage and the resistances to get the exact current that we want. So how do we actually design these resistors in terms of making them give us the properties that we want? Well, there's a few things we need to discuss. I'll give you a few analogies first, and then I'll show you the equation, and we'll go over some of the mathematics. So in each of these examples, imagine you are walking from one class to your next class, and you have to go down a hallway. And the thing you want to think about is which of these two situations will be easier or more quicker to get to your next class. So we have a long hallway and we have a short hallway. So if you just kind of think about it, I can get to my next class quicker in the shorter hallway. So even though there's nothing in the way, because you have less distance to travel, we kind of say that a shorter hallway has less resistance because you just don't have to do as much. You don't have to walk as far. So based on that, we know that length is directly related to resistance. Just like if you have a longer wire, you're going to have more distance to travel through as an electron, so a shorter wire is going to be less resistive. You just have less wire to have to move through. The second example, we're going to say the lengths of those hallways are identical, but one of them is a regular sized hallway and the other has been shrunken down to the point where you have to get on all fours and crawl through it. Now I think you can probably realize that in this case, the regular hallway is less resistive. It's a little more difficult to crawl through a small tunnel as opposed to walking through a hallway. So we can also say that the cross-sectional area is inversely related to resistance. The smaller that cross-sectional area, the harder it is to get through that hallway. Just like the thinner a wire is, the harder it is for an electron to get through. The last one we're going to look at, this is kind of like the makeup of the wire itself or the makeup of the material. But in this case, I'm going to assume you have a hallway, same length, same cross-sectional area. In one case, it just naturally has something, whatever this, I don't know, something on the ceiling and on the floor that's blocking the way. And in the second case, you have much, much more of it. So you can tell here that just based on this gunk or whatever is in this hallway, it's going to be easier to get through the top hallway. This one's a little bit trickier. What we're really saying is the molecular structure or the internal makeup. What we're really saying is the natural resistivity. So as we went back to before, like there's always a natural resistance to different objects. Well, some objects have a fairly high natural resistance, and that's why we use them in resistors. But the actual internal structure of these hallways will make it more or less difficult. So we say the molecular structure, the natural resistivity is directly related. So the lower the natural resistance, the easier it is for electrons to get through, and the higher the natural resistance, the more difficult it is to get through. So now that we kind of have a visual understanding of this, we can go ahead and we can take a look at the actual equation. If you want to design a resistor, you're going to use the following equation. R equals rho, that's the Greek symbol rho, it looks like a P, rho L divided by A, where R is the resistance. Now the unit for resistance is the ohm, OHM. It's like an upside down horseshoe kind of symbol. Okay, it's the omega symbol in Greek. So R is resistance measured in ohms. That rho, which you could certainly write as a P, but rho is the resistivity constant. Now that is something you'll be given. You'll be given like a list of these values, much like the triboelectric series and things along those lines. We just have lists that give us the resistivity constant of several different materials. That is measured in ohm meters, not ohms per meter, ohm meters. L is the length of the resistor. How long is that wire? Measured in meters. And A is the cross-sectional area of that resistor or of that wire in square meters. Okay, so make sure you have these down. Make sure you understand that that horseshoe symbol is an ohm, because you're going to see that quite frequently. And we'll go into a few examples so we can understand how to use this to design a resistor with specific properties that we're looking for.